Yeah, we'd all love it to be like 0 is the worst you can get and 1 is the best you can get. Or no, the other way around. 0 is usually the best you can get when it comes to error. 1's the worst you can get. And then it would be all nicely normalized and we could give it an assigned meaning. There's not really a known meaning for it. It's just how far your expectations deviate from your predictions, or how your predictions deviate from expectations. What that means is totally problem dependent. In this case, it depends entirely on the meaning of the data, which apparently was the price of housing in houses in Boston in thousands of dollars in 1990 something. Okay. Another significant issue that came up with that was pretend the horizontal axis is features. Now, we had 13 features. I only have one axis to work with here, so pretend this is 13 dimensions right there. And we'll put labels up here. And suppose your data looks kind of like this. That's nearly linear data, isn't it? And then if you fitted it, what's the past tense of fit? It's got to be fat, isn't it? Okay. If you had fat the data with this green line here, then it would look about like that. Now, suppose there was an outlier in our data such that this one feature were 10 times what it was supposed to be, like that. And now we fit the data. What's the error going to be if we fitted it like this? Yeah, well, I mean, it'd be this plus this plus this plus this plus this plus this, all squared, plus that, where that goes all the way up until those lines intersect, right? Squared, which is going to be enormous, which is going to be smaller, that, or this one. Now in this case, the error is going to be 0 from that one on the right, but it's going to be kind of big there, that squared plus 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 that squared. Which do you suppose is going to have the bigger error? The first one, because when you square things, big becomes humongous, right? And a bunch of small things, not so bad. Well, as it happens, I gathered my housing data from the UCI repository about a decade ago, because that's when I was a student and that's when I needed data and was gathering it up. And since then, somebody discovered that there's an outlier that was probably misrecorded in the housing data. And a lot of you guys discovered that. I didn't know about it. So again, I was camping. I apologize for all the chaos. And I'm actually very impressed with the class that you hunted that down and resolved the issue and all that. But the fact that there was one outlier completely threw off linear regression. And I ended up having to say, this is the correct answer. This is what gives you a root mean squared error of about 38 point something. And most of you were getting 38 point something because I wasn't expecting you to fix the outliers because I didn't think there were any. And I didn't even know it was a problem until somebody did some analysis and said, you know, that's a ridiculously large error for this data set. And I thought about it, and it turns out totally is. You should never get error that big, given the fact that the labels themselves actually range from, let's see what they do range from. Plus stats, housing labels. Okay. The labels themselves have a mean of 22 and a deviation of 9. So, you know, on average, they're going from 22 minus 9 to 22 plus 9. And yet we were getting an average deviation from the model of 38. Do you see how bad that is? That's abysmal. So in fact, the assignment was to get really bad results. If your OLS was correctly implemented, your results stinked. Stank? Stunked? whatever the past tense of stink is. My conjunctifier, what's it called? What's it called when you take a verb and you move it into different tenses? Conjugate, my conjugifier is not working today. Okay. If you remove that one outlier, which happened to be the last line in the data set, you got a lot lower error, a deviation of about 4 from the model, which means the model was actually finally fitting to the data. So lessons learned. 1, don't trust Dr. Gashler's data. 2, just do what the assignment said and I'll count it as right. Now, the real lessons are, hey, linear regression stinks with outliers. It's important to do some outlier removal before you do linear regression, or else bad things will happen. And that's kind of a good intro to, hey, let's move into nonlinear models. Suppose we had data that looked like this, and we had a model that didn't have to fit a straight line, but it could actually bend. How much better could we do? Imagine our model could just do this. Well, now we could get really great error without even fixing the outlier, right? Is that a good thing or a bad thing?
It can be bad because then you can fit any data.
Yeah. In fact, it can be bad, and it often is. So a very important lesson in machine learning is, hey, a more flexible model is not necessarily a good thing. And I really want to lead in with that caution. It's kind of like fixing the random number generator in Java so that you get correct results when you do the wrong thing. Is that a good thing or a bad thing? It's kind of nice when it just works, but it's actually bad for learning programmers, right? So nonlinear models will do a much greater job. And interestingly, this will still work, though. It'll make good predictions, at least in the region where the data is good. It'll make terrible predictions over in this region because it's only got this one training pattern that totally threw it off. But I guess the point is nonlinear models are way more flexible than linear models. If you happen to have data that's not linear, right? What if you have data that actually looks like that? Pretend those are all dots and not streaks. Then you'd really want a model that kind of goes like that, wouldn't you? Rather than one that goes like this. Because while, yes, that makes decent predictions, humans can tell there's some pretty clear trends here, and we'd really like to fit to those real trends. And so nonlinear models have value, and that's kind of where we're going next. And then we'll talk about why nonlinear models make sense and are important and things like that. Okay. Those are the major points I got out of this assignment. That, and I think I've got you all on track with me, and we know how to do assignments and get them passed off and all of those issues. Anybody else learn anything or want to talk about something that happened in that assignment with me or with us? Yeah. Yeah.
And how does that even,
I'm still...
What's the right answer?
Okay. The right answer, without fixing the outliers, if you just fit a linear model, if you just fit a linear model to the data, it ended up being between about 37.9 and 41.8-ish. Those are kind of vague impressions. I'm not sure exactly what they were, but it was right around that range. Those who fixed the outlier and had a correct OLS were getting like 4.6 to 5.2-ish. That's what I've been, I think probably 3/4 of the class were getting these numbers and 1/4 of you were getting those numbers. And then if you were out of those ranges, and mostly I've contacted you, some I have yet to contact about it. And yeah, I think that's about it. Is anybody getting anything vastly different and think you're right?
I mean, I got like 8.
I didn't see many people getting 8. I saw 1 or 2. Did anybody else get around 8-ish?
I got it around 10 for a little while, but it ended up being a 5.
Okay. I bet he wants to know what your bug was.
So,
We'd all like, you want to tell us, or you want to just, you can talk to him afterwards, whatever.
It was in the cross-validation. I just had a bug where instead of, I think it was, I was comparing the fitted values with, it was always comparing with my very first section of the cross-validation. Like I just was drawn the wrong matrix.
Okay. But by and large, almost all of the bugs all of the bugs I've seen after the unit test were due to cross-validation. So if you implemented the unit test as instructed in the instructions, basically your OLS is rock solid, and that means your bug is in the cross-validation. I should have added a unit test for cross-validation. Well, I did as an afterthought, but it wasn't a very strong one. So yeah, if your numbers still aren't in that range, look really closely at your cross-validation. I'm 80% sure that's where all your bugs are. Of course, I'm sometimes wrong, so I don't know. But if you pass that unit test and if it's directly computing the same values that you put in, and you've tried it with a few different dimensionality sizes, if your unit test for OLS is strong, at least you can be confident your OLS is right? I mean, that's kind of the point of the unit test. Therefore, the only other likely source of bugs is the cross-validation, so let's look together at that. Okay, and I'll do office hours after class today, and I think we can get this assignment out of the way and moving on to the next stuff. Anything else anyone want to say? Anybody else learn anything? Yes?
Just a quick question. So like the prediction ended up, I think so, being like the activation of the one layer we were using.
Yes.
So I know that was a protected, were you just supposed to make a getter for that to be able to use it somewhere else, or was it to be able to not need it to be?
I'm not sure I even really thought about it that well. Let's see. In the instructions, schedule assignment 1. Okay, so I had you write this layer class, and there's an activation vector, and that vector is protected. There we go. That one's protected. And the question is, how do you get at that? I was thinking was it activate method or your feed forward method? What did I have you call it? Activate? Okay. I was thinking your activate method should return a reference to a vec. And basically you'd return this vec because that's the one you'd fill up with the numbers, so you're not allocating new buffers every time. That way you'd never really need a getter because your activate method itself would return that. At least that's what I was thinking. I don't want to dictate the architecture too much though, because I do want it to be clear that there's not one right way to build these models. If you do the math right, the models are good, and if you find some way to make it more convenient, your design trumps my intended design. But at least what I was thinking is you activate this function. Wait a minute, how can you return something if it's void? Clearly I didn't think about it very well. I guess I was thinking you were going to change that to a vec reference. My bad. There you go. Sorry for not clarifying how to do that. Getter is a good solution, or whatever you want to do.
do we need that letter or the activation variable?
So the whole point of this is to say, in the next assignment, and this is what we're building up to, and by next assignment I mean the next coding assignment. There we go, which is due on Washington's birthday. By the way, that doesn't mean you have to take off Washington's birthday to work on my assignment. You're supposed to get it done before Washington's birthday. Okay, we're going to be taking our layer class, and we're going to add another vector to it called blame. And I'm going to go in and change the signature of that activate method so it returns a vector reference, because I think that's a good way to do it. And we'll add this thing called backprop and a thing called update gradient. So we'll now have 3 methods instead of 1 in our layer class. And with these 3 methods, we can train a multi-layer neural network, which will be able to handle nonlinear problems and fit to it really well. So that's where we're going with this. Thanks for pointing that out. This signature is insufficient because what's the point of activating if you can't get to the activation? So yeah, I need to update that.
Same thing with blame? Or?
What's that? Same thing with blame? No, you never really need the blame. You only set the blame. Basically, the activation's the only thing you'll get.
So why you put to do with the blame variable or just store some number somewhere?
Basically, the last layer in your neural net, you will assign blame to it. That's basically where you tell it, bad job, and it will update itself in response to the blame you give it. We'll start talking about what this is all about and where it comes from, and that's what I want to do right now. Yeah, go ahead.
Do we need to pass the variable to the inherited class? Or
Which variable?
the activation and blame? So if layer linear inherit from layer,
Oh.
does it need access to the variable or not?
Yes, because I'm indicated that they are protected, by default, child classes will have access to those. So if you're using a non-object-oriented programming language, then your layer linear should have a reference to a layer object. Or you could stick those in all of your layer types. Basically, all of your layer types will need an activation and a blame. That's the common thing among all types of layers. And we're going to implement some other types of layers, some nonlinear layers as well. And that's where we're going. Did that answer that? Okay. Now let's talk about some calculus. Everybody remember calculus perfectly? So I can just skip over that. Okay. My experience is everybody has this vague recollection of once having been able to do it, and nobody remembers quite how to do it or what it's good for. Is that about where you are in calculus? Like if I talk about calculus, you think you can keep up, but you'd kind of like me to go over how to do it again. Based on the silence, I'll guess, yeah, that's exactly right, Dr. Gashler. Okay. This is a curve. This is a tangent line, right? Okay. Now, imagine we're in hyperdimensional space where instead of a curve, this is a rolling hill covered with snow. It doesn't have to be covered with snow. It's just a rolling hill. But we might want to go tobogganing down it anyway, which is why it's covered with snow. And this line is really an analogy for a tangent hyperplane. So if it's a two-dimensional surface, two-dimensional nonlinear surface, then this green line is really a two-dimensional plane. And if this is a 47-dimensional nonlinear surface, which I can represent by going like this, then this green line represents a 47-dimensional flat plane. Okay, with me? Now, in calculus, we calculate the tangent to a curve by computing the derivative. I'm betting that most of you remember polynomials, because when I was in Algebra 1, we hammered polynomials really hard. When I was in calculus, we did a lot of that. So if I were to say 3 plus 2x plus 4x squared, and if I were to pretend that that were the equation of this line, what would be the equation of this tangent plane?